So let's talk a little bit more about finding time constants for our first order circuits. So we need to look at the circuit configuration in the final position, which is where the transient will take place. If we have multiple inductors or capacitors, then we need to combine them, series or parallel combinations into a single equivalent inductor or an equivalent capacitor. Then we need to know what is the Thevenin or Norton equivalent resistance from the perspective of the inductor or capacitor. So to elaborate a little bit on that, basically we imagine that we disconnect the inductor or capacitor, and find R Thevenin from those pins, or looking into those pins. I might say looking into R Thevenin, looking into those pins. And then finally we calculate the time constant, which of course is R times C for capacitive circuits and L divided by R for inductive circuits. So let's have a look at an example problem. So this is 7.37 from the textbook. It asks us to calculate the current I that flows in this branch here, which contains an inductor. And we have a switch which will toggle at time 0 from one position to the other. So to solve this, we have a few things that we need to do. So firstly, we need to find the initial value of the current. So I'm just going to draw what the circuit will look like with the switch in the initial position. So in the initial position, we have this 120 ohm resistor, this 800 volt source, which will go across through this 40 ohm resistor, the 10 ohm resistor, and then the inductor I'm just going to replace with a short circuit, because for steady state DC it just passes straight through inductors. And we are trying to find the current I0 here. So obviously there's a few ways that we could analyze this, but what I'm going to do is just use nodal analysis. So I'm going to define a node voltage here, V1, and use KCL and get an equation. So KCL, current's leaving to the left-hand side. This is V1 minus 800 divided by 120. Current's leaving down the vertical branch is V1 divide 40. And on the rightward branch is V1 divided by 10. And so that's equal to 0. So I can bring together all my coefficients of V1, and so they are these times V1, and the right hand side will be 800 divided by 120. So we just get out the calculator, and so right hand side, 800 divided 120, 6.66, that divided by the term in brackets. So that's 1 over 120 plus 1 over 40 plus 1 over 10 is 50. So V1 is equal to 50 volts. Therefore, our initial current I0 is Ohm's law, V1 divided by 10. So 50 volts divided by 10 ohms is 5 amps. Okay, we also need to know the final configuration of this circuit. So the final configuration, if we look at the way that this switch operates, effectively it will take this current source and kind of connect it into the circuit. So that would be now the new source of energy. So just redrawing the circuit in the final configuration, here's what we will have. So we have current source 50 amps, which has the 8 ohm resistor. The voltage source is disconnected now. There's a right hand side has that 40 ohm resistor, that 10 ohm resistor, and our inductor, I'll just draw it like that for now, because we're also going to need it for the time constant. So this will be the final configuration of our circuit. So after the switch has changed, and we need to know what is the current here. That would be our final current. So to calculate the final current, we consider the inductor to be a short circuit. I should just label, by the way, the inductor is 40 millihenries, so I'll label that on here too. To find IF, replace the inductor with a short. So it becomes even a little bit simpler. It will be just the following: 50 amps in parallel with 8 ohms, in parallel with 40 ohms, in parallel with 10 ohms. So our equivalent resistance, as seen by that current source, is going to be 1 over 8 plus 1 over 40 plus 1 over 10, all to the power of minus 1. So again, bear with me while I just quickly calculate that. And I get 4 ohms. So what the current source sees is the following. I'm doing this just to get a voltage. So I have 4 ohms, 50 amps, and I want to know what is the voltage here. So easy calculation by Ohm's law. 4 times 50 is 200 volts. So looking back at my circuit diagram, the current that I'm trying to solve for here is IF, and I have just figured out that this voltage here is 200 with respect to a ground. So therefore my final current will be that 200 volts over the 10 ohm resistor, so that would be 20 amps. So now I have the initial and the final current. The other piece that I need is the time constant. So here we have to be a little bit careful because what we actually need is the time constant, which is determined by a resistance that the inductor sees. So I'm going to just copy this circuit down here again. And I'm going to pose the question of the Thevenin equivalent resistance as seen by the inductor. So find the Thevenin resistance as seen by the inductor. So if I take my inductor and I take these pins here, so I've got like terminals A and B, and I'm looking into my circuit, what is the Thevenin resistance that you see if you look into the circuit here? So remember, we turn off our independent sources. If we have dependent sources, then we need to calculate, or we need to apply a test source to that. We could also find it by doing open circuit voltage and a short circuit current. So we've got a few strategies for finding the Thevenin resistance. But the easiest one would be to deactivate the independent sources, and simplify. So turning the current source off, basically putting that to 0 amps, just creates an open circuit. So we end up with that. So therefore, the Thevenin resistance as seen by the inductor, looking at the circuit, is going to be 10 in series with that 8 in parallel with 40. So that would be 10 plus, so the product divided by the sum, which is, bear with me once more while I calculate this, 10 plus, so 8 times 40, divide 8 plus 40. That is 16.6667 ohms for my Thevenin resistance. So therefore we are ready to calculate the time constant. So my time constant for an inductive circuit is L divided by R. So my inductance was 40 millihenries. So that's 0.04 divided by the Thevenin resistance that I just calculated. So once again, bear with me. And the answer is 2.4 milliseconds. 2.4 milliseconds as the time constant. So we're pretty much there at this point, so we can write down our general form for the step response. So that is I final plus I initial subtract I final times e to the minus t over tau. Let's sub in the numbers that we have. So final was 20 amps. The initial was 5 amps. So 5 minus 20, e to the negative t divided by, so it's 2.4 milliseconds, so 0.0024. And of course, we can clean up those numbers a little. So 5 minus 20 is 15. So minus 15 e to the negative t divided by our time constant. So that's 0.0024. And that's the final answer. So the bit that is perhaps a tiny little bit tricky that you need to be aware of, when calculating time constants, what really matters is the resistance as seen by the energy storage element. So as seen by the inductor or as seen by the capacitor. So basically disconnect that energy storage element and then analyze the circuit like looking into those terminals. So it's a Thevenin resistance, so go back and refresh yourself if you're not sure on how to calculate that. But for many cases, you'll be able to just deactivate the independent sources and then simplify the resulting resistor network.